April. Welcome to the talk of the senior physicist group. The senior physicist group is completely voluntary. We have no role and we have no treasury or dues. Anyway, we also have talks. We tried to schedule them on the third Wednesday of the month, but we are very accommodating because it is somewhat difficult to get speakers, and we do everything we can to accommodate them. We also have planning meeting, which is held on the first Thursday of the month, and anyone is welcome to join. I would suggest go to Google and look for the senior physicist group, and or you can send me an email, dnovotny2@verizon.net, and I will try and give you directions, although sometimes I'm having a hard time following them myself. Anyway, with regard to the senior physicist group, we do post the slides, and they are posted on a site. And there again, if you go to say Outlook and look for APS space SPG slides or something like that, you can get the link. Okay, let's see. Oh, one other thing. We have been in the past meeting at the American Center for Physics, which was a building in College Park, but it has been sold by the American Physical Society, or the American Institute of Physics, which is the overlook society. Anyway, and the APS is reducing their staff. So after May, we will no longer be in that building, but we will be broadcasting from the physics department at the University of Maryland. So let's see. With that, I wanted to make a brief talk as comment. Our talk today is about time. And if you ask yourself, what is time? You find it's a relatively difficult question to ask or to answer. Basically, time is a parameter, and it's measured between this and that. It's a duration. So anyway, there is no standard reference material for time. I mean, the best we could do would be to refer to thorium-226, but that's not accessible. At least the nuclear levels are not accessible to normal people. Anyway, with that introduction, I'm going to turn the talk over to Jerry Stombacken, who will introduce our speaker.
Okay, thank you, Don. I'm very glad to introduce our speaker, Dr. Jun Ye. He is a fellow of JILA, which is a joint institute between the National Institute of Standards and Technology and the University of Colorado at Boulder. He is a fellow of NIST and a member of the National Academy of Science. His research focuses on the development of new tools for light-matter interactions and their applications in precision measurement, quantum science, and frequency metrology. He has co-authored over 400 scientific papers and delivered 700 invited talks, 701 after today. Among his awards and honors are 5 gold medals from the U.S. Commerce Department, the N.F. Ramsey Prize from APS, II Robbie Award from IEEE, II Robbie Prize from APS, and the N.F. Meggers Award from OSA. His recent honors include Breakthrough Prize in Fundamental Physics, Niels Bohr Institute Medal of Honor, Herbert Walther Award, and Vannevar Bush Fellowship. The webpage for the research group includes highlights for many highly talented, enthusiastic young researchers, and it is available at jila.colorado.edu/YeLabs. With that, here's our speaker. Thank you.
Well, thank you, Jerry, and Don for the very generous introduction and the history about this senior physicists group at APS. And I feel honored that you asked me to come in to tell you a story about making clocks, making atomic clocks. But as I discussed during the initial chat, that I will tell you a lot about the sort of a fun physics we're exploring with clocks and also during the process of making clocks. And this, I would argue, is a revolution in timekeeping that's ongoing. And it's a really exciting pathway where laser physics, quantum science, and precision metrology all come together to set a new frontiers of precision metrology, but also providing new opportunities to explore new physics. So hopefully in the next 15 minutes or so, that we get to enjoy that story together. And if you have questions, I don't mind being interrupted at all. You just have to let me know, since I'll be focused on the screen. Maybe Jerry can can sort of monitor the traffic of if there's questions. We can also entertain the questions at the end of my talk. So let's get started. I chose this title, try to emphasize the importance of laser for building the modern generation of so-called optical atomic clocks. And also we'll make a connection to even using lasers to study nucleus now, that we can open a nuclear clock as a future pathway for timekeeping. And I just give you a quick slide on a summary of the state-of-the-art clock performance today. In terms of the measurement precision, that we care about clock stabilities, 1 second, what is the measurement in the fractional frequencies instability at a 1 second averaging time? How does it average, and so on? And you can see on the upper left corner, there's a number called Allen deviation, which shows at a 1 second, we cannot achieve 4 × 10⁻18 level of precision. And this number has been recently revised to 1 × 10⁻18 at 1 second. And will average down as a square root of the measurement time, going down to, for example, by the time you go to 10⁵ seconds of averaging time, you can enter the measurement precision of 10⁻20. And just to remind you, and I'm sorry for a little typo here, 10⁻20 is actually represents the gravitational redshift as predicted by Einstein's general relativity that is caused by the Earth gravity that will cause time being different when you raise the clock up and down on the surface of the Earth by 100 micron. It will represent a 10⁻20 frequency, fractional frequency shift of the time of the clock. So that's a pretty high level of precision. The typical GPS measurement precision would be at the level of 10⁻13, 10⁻14, and average it down to 10⁻15. In terms of accuracy, which means how you can compare your clocks between different laboratories, how well you can define the clock, eventually the total systematic uncertainties will be needed to allow us to, say, redefine the time based on this new generation of optical atomic clocks from the current definition of the time based on the cesium microwave standards. And as you can see, both neutral atom-based optical atomic clock as well as ion-based optical atomic clock have reached the systematic uncertainty below 1 part 10⁻18. And that sets the stage for the near future redefinition of time if more worldwide comparisons of various different state-of-the-art clocks to be made, so that internationally we have a good network of clocks that can all be synchronized and can be compared in a reliable way. And that's ongoing because the infrastructure that's currently in existence for comparing clocks are mostly for microwave clocks, for cesium clocks, for GPS, and so on. And the level of precision is simply not good enough to compare these new generation of optical atomic clocks. And we have to develop new technologies how to compare these optical atomic clocks across distance and eventually across continents. Entanglement, you may have heard a lot of excitement recently about quantum, the second 2.0 quantum revolution, the idea of that you can entangle multiple atoms to cancel quantum noise. And this is a key piece of technology where people are using to build a quantum computer, to build the secure quantum communications. And I think one key application of quantum entanglement is in fact to push the frontiers of a quantum metrology, where at the state-of-the-art level, we want to start to implement entanglement into our clocks and see how we can benefit from the spin-spin entanglement can allow you to hide away some of the fundamental quantum noise of independent spins. And this is, you can see some sort of initial demonstration experiments starting to come where at the level of 10 to minus 17, not quite at the state of the art I'm talking about in the precision at the upper left corner, but nevertheless, you can see that several different platforms start to see that when you use entanglement, you can achieve performance better than if these atoms are left to be independent. And all this, I will be coming around, tell you a little bit in a more detailed fashion of how we achieve these various different goals, and altogether tell you what's the future, what we are moving towards. So let me start with telling you a little bit of a time scale, just to step back, to relax a little bit, enjoy some of the very easy to understand physics concepts. And this is atomic clock is all based on a superposition of electron orbits. And here shows an animation of electron cloud oscillating back and forth around the atomic nucleus when you put it, for example, s and p orbitals in superposition. And of course, this electron evolution is happening at a very, very fast time scale, typical time scale, if I may say, on the order of a femtosecond, 10 to minus 15 seconds. And if I slow this down by 10 to the 15 times, of course, this looks like one oscillation per cycle, looks like a little pendulum in the quantum regime. On the other hand, the lifetime of the universe is 14 billion years. That's about 10 to the 18 seconds. And they take the geometrical mean between these two microscopic time scale and a macroscopic time scale is about a minute. And what is amazing that today in our laboratory, and when I say our laboratory, is a sort of a worldwide laboratory with people pushing on quantum science forward, but some of the best labs now can achieve quantum coherence at a time scale of a minute and longer. That's quite remarkable in the sense of that this midpoint means that I can think of this quantum pendulum oscillating up to this midpoint is equivalent to saying I have a classical pendulum, my grandfather's pendulum, oscillating throughout the entire age of the universe. These two, fractionally speaking, would be equivalent. And it's telling you the so-called quality factor of how many oscillations you can observe over the time scale of the pendulum is 10 to the 17, 10 to the 18 times and cycles. So if you can capture every single oscillation of the entire sort of lifetime of this pendulum, you are already making precision measurements at the level of 1 part 10 to the 18 and so on. And this is the reason why we use quantum systems with such long quantum coherence to build the modern generation of optical atomic clocks. And I also want to emphasize the clock, as we talk about today, is much more than just a timekeeping piece. But we certainly hope it is becoming now a scientific instrumentation that will allow us to explore very fundamental questions of our universe. And if you have a pair of clocks that can measure directly 10 to minus 20, 10 to minus 21, you can use them to directly measure the gravitational waves. You can set bound on unknown phenomena such as dark matter, and you hope dark matter will eventually interact with ordinary matter or ordinary field that we know of, not just through gravitational attraction, but through some other beyond standard model sort of physics interactions. And we want to build some of the most sensitive physical instruments to be able to detect the existence of dark matter through these beyond standard models interactions that we don't yet know. So this will be kind of building your best microscope and try to find what's hidden under there. And we mentioned about GPS clocks, and of course, in the future, if we have the technology to link up all these optical atomic clocks, it will provide an incredible network and also long baseline interferometer to turn these clock networks as observatory for astrophysics, where a lot of exciting discoveries are waiting for us to make. And also such network of clocks will surpass the performance of GPS clocks by quite a few orders of magnitude, maybe set the stone for eventually having a civilization that spans beyond Earth and actually conquering the entire solar system and having a GPS for the entire solar system. And also want to mention, of course, clock through general relativity is connected to geo activities because of gravitational potential and time and space. They're all connected. So by being able to measure time really well and taking these state-of-the-art clocks out of the laboratory and use them to do real field sensing may allow us to understand our changing world in a much more detailed fashion. So want to go back a little bit, telling you about how we can measure why we can build such an amazing atomic clock, and really goes back to today is actually the World Day of Quantum. Goes back to the Bohr orders theory of atomic model, where you have electron orbiting around the nucleus, and there's a prescribed those electronic orbits energy level structure is actually rigid, and the separation between different electronic orbits have a specific energy differences, and those are in principle made by the universe and over many billions of years, and it's all set in stone, right? These are the very basic rules of quantum physics that we rely on to build a very precise atomic clock. And I call this as a Bohr's certainty principle, because this is where we can be confident the clock I make in Boulder, Colorado can be the same as the clock you make in Washington, D.C. It's because we are based on the same quantum mechanical principle, so far as we take into account, for example, general relativity effects. And on the other hand, you ask yourself, well, we also know the very famous uncertainty principle of Heisenberg's uncertainty principle of quantum mechanics. And some people, myself included, may even argue the only thing that truly distinguishes quantum from classical physics is this uncertainty principle, or is this so-called quantum noise. And so where does that quantum noise enter in clock? Well, that's because in order to measure the energy difference between these different electronic orbitals, you have to put the quantum system, the atom electronic system, into the so-called quantum superposition. The superposition is between a ground and excited state. These are the two clock states, G and E, and we often use a fictitious sphere called a Bloch sphere to represent a two-level system. G, ground state, excited state as a south pole and a north pole. The superposition of quantum mechanics saying this vector can occupy, in principle, any point on the sphere. But if I suppose I put them in a coherent superposition of ground state and excited state on this equatorial plane, meaning exactly half and half, then I can actually watch the phase evolution between the ground state and excited state, because the energy difference is E, and then multiply with time t will give rise to this phase evolution in this coherent superposition state. But when I want to go in after a certain time, I want to go in to measure the time evolution. I want to measure this phase really, really precisely. How do I measure the phase really precisely? I'm trying to read out whether the atom is in the ground state or excited state, because those are the two eigenstates of the Hamiltonian that I can read. But then there's a fundamental uncertainty that in coherent superposition state, when I try to go in and measure which state this this atom is actually in, I will not be able to know a priori whether it's in ground or excited state. And that's really is the fundamental so-called quantum noise. Another way of thinking is pictorially, you can think of there's a little blob of uncertainty that's associated with time error on this equator. And so this provides this fundamental noise of quantum mechanical uncertainty to my time precision. So it's interesting, right? At the same time, quantum mechanics tells us we can make the most precise clock. At the same time, quantum mechanics also tells us there's a limit to the precision because of a quantum uncertainty principle. So it's like really beautiful conflict of this fundamental nature of quantum mechanics that giving us both enabling, but you can say interesting challenges at the same time. But it's the interesting challenge part is where what's driving the so-called second quantum revolution right now. And in order to probe the atomic evolution, especially for the so-called optical atomic clock, we use lasers to probe the superposition. So we have to build a very, very good phase-stable laser to be able to look at this atomic needle of where the superposition is. And another kind of a quick animation that can show you this principle is that imagine this, you have this quantum pendulum going swinging back and forth. And if you want to be able to see such coherence.
How nice see you.
Yeah, she says we're working.
Sorry. It's okay. Yeah, continue. And so in order to be able to catch that quantum coherence, you want to build a stable laser that's represented by this white sinusoidal oscillatory curve. You want to make sure the sinusoidal curve of the laser phase to be as well matched to the atomic phase over time as possible to be able to actually see clearly how the atomic evolution is happening over time. So this tells us we need to build a very long coherence time laser to be able to match up with atomic coherence to be able to really probe such fundamental quantum system. And so let's talk about laser a little bit. This is a very broad spectrum of electromagnetic spectrum spanning from radio waves all the way out to X-rays. The visible part of the spectrum where we use to build optical atomic clock is a very small sliver of the entire spectrum here. And furthermore, if I zoom in from this entire visible spectrum to a little color of 700 nanometer, this happened to be a laser I use to probe my atomic clock, strontium atoms. And this is provided by a little semiconductor chip, a semiconductor diode laser, which typically emits with on a line width of a few hundred megahertz, which is about 1 million times narrower than the entire visible spectrum. So zoom in from a visible spectrum by 1 million times, you get a laser like this. And this laser has too broad a frequency spectrum to be able to probe very narrow optical transitions that I want to use as an optical atomic clock. So we have to work on the laser technologies to zooming in to narrow down the optical spectrum. And we have to thank for, of course, the pioneers such as John Hall and many others who have been working on laser stabilization since 1960s and 70s. And this is a cavity, it's called a Fabry-Perot cavity that in Jan Ho's laboratory back in the 80s and 90s, where they developed the technology of stabilizing lasers onto a pair of mirrors, which is attached to a ultra low expansion glasses. And you use this very stable Fabry-Perot cavity to stabilize laser frequency down to about 1 kilohertz or so. And this allows you to zoom in the laser spectrum by another 1 million times, such that you can now have laser line width on a few kilohertz also at the time, and laid the foundational technical foundation for laser stabilization later on led to the technology to be adopted by LIGO and led to the successful observation of gravitational waves. It's thanks to this technology that's actually developed on this device called a puncture Hall locking. And for that, it's still not quite sufficient to really chase down the quantum coherence I was telling you about, where you have a 10 to the 17 cycles of oscillations that you want to watch. So we need to zoom in yet another 1,000,000 times. And this now takes the modern version of a Fabry-Perot cavity. It's made out of a silicon crystal cavity. Silicon actually has some very unique physical properties, such as cooling down to certain temperatures, like 124 Kelvin or 16 Kelvin. Its a thermal expansion coefficient crosses 0. And so you can use silicon cavities to build a super stable Fabry-Perot interferometer. And we can use this now to stabilize lasers down to a laser line width of just a few millihertz at 1.5 microns. This represents another 1,000,000 times zooming in from a few kilohertz to a few millihertz. And with those 3 times of a 1,000,000 times zooming in, we are now talking about from a visible spectrum zooming in by 10 to the 18 times, getting down to a laser line width of a few millihertz. And this is the best state of the art of a laser spectrum we have today. And if you translate this a few millihertz line width to coherence time, you can immediately calculate the coherence time is approaching almost a minute. And it's kind of interesting to also translate the temporal coherence to spatial coherence, where if you just multiply by speed of the light, you know that you can turn the temporal coherence of tens of seconds into spatial coherence of the distance between Earth and the Moon multiplied by a factor of 100. And in another way of saying, the distance between Earth and the Moon is about 10 to the 15 optical waves. And we can now, the optical coherence is so good, it would allow you to measure the distance between the Earth and the Moon down to less than 100 nanometers, like the size of a bacteria. And we are working on technology where hopefully we can extend such a laser coherence in both time and space, that over the entire astronomical unit between Earth and the Sun, we would in one day be able to feature a laser with coherence time or coherence length over that scale. And of course, such technology is incredibly useful if you have these lasers on board of satellites, and you can pretty much control as you shoot laser beams back and forth between those satellites down to a fraction of the wavelengths if these lasers are coherent, spanning hundreds or millions of kilometers between satellites. So let me now move on to the atom side. I told you a little bit of a brief story about how do we get really stable phase coherent lasers. Now let's talk about how do we apply these lasers to atoms to get the time out of them. And time, of course, is relative, and we know from Einstein's relativity. And you really have to be careful when you're making observation if the particles, like is shown here as bouncing around in a hot vapor cell. And then, of course, compared to a stationary observer such as us, the clock is in the moving clock appear to be moving slower, and all these atoms have a different speeds, and that will lead to a mistake. At the same time, there's also the general relativity where the space-time can be curved due to the existence of heavy body nearby. And we all live on Earth. There's a curvature caused by the Earth. That's the reason why we can observe redshift by comparing clocks at different elevations. So if you, in the modern atomic clock, if you want to compare clocks at the level of 10 to minus 18, that represents a centimeter difference in height. And so therefore, having atoms moving around in a vapor cell not only will contribute the so-called time dilation due to motion, but also time dilation due to gravitation. And if you are not careful, you can observe lots of atoms, but none of them would agree with each other in terms of their time. So we have to solve this problem, and actually it's kind of interesting to go back a little bit to really celebrate these pioneers who give us the technology of the so-called laser cooling and trapping. And I will name a few of these heroes here. This is the Dave Weiland's group in the 1990s, they have been working on single trapped mercury ions together with Jim Berquist, for example, most notably. They were able to trap a single mercury ions in a Paul trap, and the trapping potential is sufficient such that they can reach the so-called Lamb-Dickey regime, where the laser probing these ions will no longer experience Doppler shifts and as well as recoil shifts. And they can cool down this 1 mercury ions to make a fantastic optical atomic clock at the time. This is the turn of the century, and already at the time, the precision level is comparable to at the time state-of-the-art cesium fountain clocks. But of course, one would imagine it would be really powerful if one can just repeat this successful story by having many ions together. That's one way of doing it, building multiple ion traps. Or you can say, what if we just move on to neutral atoms and instead of charged particles, you can pack many more neutral atoms together, and that allow you to build potentially much more precise clocks because you have a much better signal to noise ratio by averaging lots of atoms. And this, in some sense, this triggered the technology of laser cooling in a more general sense, and as shown by these 3 gentlemen, Steve Chu, Claude Cohen-Tanuyji, and Bill Phillips, where if you have an original vapor cell that with hot atoms and you tune the laser frequency just about right and shining the lasers against these atoms from 3 orthogonal directions, if they tune the frequency just about right, you can push the atoms back against their motional direction, and in some sense causing viscous force against the motion. And if you can also create this trapping potential, then you can actually load all these atoms with exceedingly low temperatures in a particular spatial location. And this technology developed in the 1980s and 90s have now matured. We can teach this technology to undergraduate students, and it's a kind of amazing refrigerator that the hot atoms at the temperatures of hundreds of Kelvin can be cooled down to millikelvin or microkelvin in just a fraction of time, a second. And so it's amazing technology to put these atoms, essentially take all the entropy out of the system and replace it with scattered photons, that's where the entropy escapes to. And then put a collection of millions of these atoms, cold atoms, located in a particular spot in your vacuum chamber. And this technology soon led to the creation of a new state of matter called Bose-Einstein condensation. Cornell, Kedley, and Wyman showed bosons love to condense into a single quantum mechanical ground state, forming a BEC that's almost a macroscopic quantum object people can almost observe with naked eyes. And this also very quickly followed by another major breakthrough that was this time was done by Professor Deborah Jing, a JILA fellow. Unfortunately, she passed away about 9 years ago now already. She was the first to create the so-called Fermi degeneracy of atoms, where the fermions are notoriously known to be wanting to avoid each other. So when you cool them down to very low temperature, when you remove their entropies, they very orderly organize themselves to be occupying 1 quantum state at a time, and only one fermion can occupy 1 quantum state, and they build up such that they formulate the so-called Fermi C, and you can define this Fermi surface and so on. That's the highest level of Fermi energy. The reason I'm talking about this is this created an amazing opportunity where over a fraction of seconds, or maybe just a few seconds, you can create a quantum gas of these atoms with such low entropy. Now you can start to think about, what if I make an artificial crystal? This is a crystal made out of the interfering laser beams. And because the entropy of these atoms is so low, I would be able to now start to put 1 atom per site, just as I've shown here. And this is the so-called optical lattice. And so this is as close as you can potentially have, where you can have tens of thousands or maybe 1 million atoms all trapped in these optical lattices. And every atom in principle will experience exactly the same trapping potential. That's not exactly true, but we can find ways to mitigate that problem. And you can now think about all these little Bloch spheres represented by each atom, and you can have them average down this little quantum noise by just having measurements over in parallel over millions of copies of these. And that's the basic that's the basic motivation of building the neutral atom optical lattice clock. Is I'm going to use AC stock shift to create spatially independent energy level shifts so that you can create this kind of a trapping potential for atoms to be trapped there. One important consideration is that when you create AC stock shift between the atomic levels, you want to choose the wavelengths carefully, such that that the ground state and excited state, if they experience different AC stock shifts, then in principle the atoms inside these optical traps will be distorted in energy levels, and that's always true. That's the whole reason why we can trap them. But if the ground state and excited state experience very, very different AC stock shifts, it's as if you look at these original Bohr model, it's as if the energy level between ground state and excited state not depend on where the atom is in the location of this trap. When you're at the bottom of the trap, you have the biggest intensity, you have the biggest distortion. When you're at the shallow part of the optical trap, you have less distortion, the energy difference is less different, and so on. And this will create a problem, right? You solve the motional problem, but you're replaced with a position-dependent AC stock shift, differential shifts between the atomic energy levels. And this problem was solved at the turn of the century by two independent proposals, one at Caltech. Jeff Kimball, at the time, I was his postdoc at Caltech in Pasadena. The other independently came from Professor Hidetoshi Katori's group at the University of Tokyo, proposing this idea and demonstrating the idea that you can trap these atoms in a so-called magical wavelength. And in physics, it sounds really funny to say magic, but this is really almost feels too good to be true, that you can find a wavelength where the AC stock shift of the ground state and excited state are exactly matched. If you do that, you're creating the trapping potential to be identical between the ground state and excited state. So even though atoms are trapped, even though each state, ground state and excited state, have experienced the distortion of their energy levels, but differentially, the difference between the two states remain the same. And you can look at the picture now, every atom looks like the same energy shifts again, even though they are distorted, but at least for these two atomic states, that's special for building my clock, the energy level is undistorted. And that's a key concept that allows us to use many, many atoms together for building this optical lattice clock. So with that, these are the key ingredients that I think that we have demonstrated. And this goes back to the beginning of my talk that showed the slide where two atomic clocks, for example, positioned by just a few hundred microns apart, you can actually start to measure the time difference between them at the level of 10 to minus 20. This represents the tiniest gravitational redshift that's ever been measured in the laboratory. But the point is really, as we continue to push on this, it's kind of a really interesting time. Like, what if we push this down by another factor of 10 or so? Then you start to get into the regime where the time over atoms that's located with their de Broglie wavelength that's extending, say, a few micron or 10 micron scale over the vertical distance will experience different time evolution. So you can see that quantum evolution of multiple atoms and so on will start to experience the effect of Earth gravity. And I think it's not at this particular moment, we are not talking about quantum gravity. We're not talking about quantization of gravity at all. We're simply talking about gravity can come in and modify how atoms can interact with each other, because the de Broglie waves and so on will actually see this very minute time dilation effects. And we are starting to explore, at least on the theory side, the consequence of that. Even though experimentally we are still factor of 10 away from reaching such precision to start to explore this emerging kind of a precision frontier. And I want to also give you a little quick break here to tell you, going back to the quantum noise I was talking about earlier, and I want to give you just a very quick slide on why Quantum 2.0 is so exciting for us right now. I mentioned the superposition, and now if I try to go back to some of the common language you might be hearing, that when we initially learned the quantum mechanics, I learned the quantum mechanics in the 90s, we didn't talk about qubits. But now every student talks about qubits, so I'm going to use a little bit of that language here. The two-level system, ground state, excited state, you can think of it's a bit, it's a quantum bit, and it can be up and down, but really superposition can be anywhere, as I mentioned in this, it can be a coherent superposition of anywhere on this Bloch sphere. So coherent superposition is not a difficult concept, even though it's very different from classical physics. But we all learned coherent superposition as a physicist, and we all take that as well, that's just a peculiarity of quantum mechanics, it's a wave and so on. But entanglement certainly is a little bit deeper and in terms of the quantum phenomena, and it's a little bit less trivial. Here I'm talking about two atoms, and they can both have a quantum noise. You don't know whether it's up or down, but I have two atoms. Whenever one atom has one particular quantum projection noise, the other atom follows exactly the same way. And that quantum entanglement is, in some sense, if you look at this two atoms, if the two atoms always follow each other with their quantum noise, then you can already imagine if I use these two atoms to build a clock, I will have two copies of a signal, but only one copy of noise. So you can win. And the same principle can be applied to quantum computers and quantum communications, because really relying on the fact that the quantum noise between these independent atoms used to be independent, now become entangled, have a strong correlation between any classical means possible. And we actually celebrated these pioneers, Espay, Clauser, and Anton Zeilinger, and so on, for their initial work on showing entanglement between photons. But this is now a concept that we are trying to adopt and use and really employ in the modern atomic clock with entangled spins, entangled atoms. And I think this is really lying at the heart of the so-called quantum speed up for sensing, communication, and computing. It's just very difficult. Entanglement is exceedingly fragile. Quantum coherence, the superposition, is already very fragile. And I mentioned it all the time about really proud of being able to achieve quantum coherence at a minute scale. But quantum entanglement is even more fragile than the quantum superposition. And that's been the difficult challenge, how to implement, and employ quantum entanglement in the state of the art of quantum sensors like clocks. And so since we're talking about clocks, let's think for a second how the entanglement comes into play a role. So as I mentioned earlier, we have a phase coherent lasers looking at a superposition of quantum state of the atom, and there's this intrinsic quantum noise of each atom. And this will allow you, if I have many, many atoms, have many, many quantum pendulums, if I average them, then the phase measurement, the so-called standard quantum limit of the phase resolution for my clock would be scaled as 1 over square root of how many particles you have. This is the typical behavior, so-called white noise, when the quantum mechanical fluctuation is completely uncorrelated. So by making n copies of the measurement, you gain by the precision by 1/square root of n. But as I mentioned earlier, if you can get those n atoms all entangled, then in principle, you can have n copies of a signal, but only one copy of a noise. Therefore, the so-called standard quantum limit of measuring the phase resolution will be enhanced by a very significant number, which is a square root of n. So that's a big gain if we want to scale up our quantum systems to push the dream of being able to connect quantum measurements, clock, and gravity all together. Microscopic quantum theory, macroscopic gravity, all of them can be manifested in quantum dynamics. It would be nice to continue to scale systems up. And one way to scale is by making n really large. The other one to scale is by entanglement, because you can go from 1/square root of n to 1/n. That's a big scaling gain. And so the question is, how do we put it spin entanglement instead of the odd clocks? And so the idea is the following. You have this noise distribution here. What if visually I can squeeze on, this is what is being squeezing, is that terminology is coming from. If I can squeeze on one quadrature of the noise contribution, and at the expense of the other quadrature, noise gets much larger. And as long as I can make precise evolution on this equatorial plane, that it's this less noisy quadrature that matters into my clock measurements. And so in principle, I should be able to squeeze that noise out of here so that I can fundamentally limit it by only Heisenberg uncertainty of a single particle, not all these particles. And so we achieve some of these goals now by using the so-called cavity QED. I don't have time to really explain in detail how this cavity QED works, except to tell you, like, very visually, you can think of, I put atoms in this optical lattice, and it's like putting atoms in an elevator. I can move them up and down. When they come to the upper levels, they are a pair of mirrors with a very high reflectivity. And you have a few photons in here looking at all these atoms in a collective fashion. Every atom will look the same way. They look to the left and the right. They look into the mirrors of themselves as well as their neighbors, and they get all confused. And in some sense, that's a way that we are doing a little bit of a spying of whether the atoms in coherent superposition of ground and excited state. And we're using this cavity QED to spy on which state they are actually on, but doing so without destroying the quantum coherence. And we can only do that by using the so-called collective physics, where you have many, many atoms in between these two mirrors, and the atoms cannot tell that one photon that's interacted with us, which one is being interacting with that photon. And so doing so, we can actually get a spin squeezing. And so now visually, you can go back to look at this block sphere, and this spying action allowed us to reduce the noise down, and it looks like this. So now you can see, because I'm gaining knowledge of whether atoms in the ground and excited state, the noise distribution gets squashed down in this quadrature. But then I have the technology to rotate the spin by 90 degrees. And that's what I'm going to do, like that. And then it evolves on the equatorial plane, which is my clock sequence. And this is the sequence that we are using now to implement spin squeezing into these clocks and make a direct clock comparison. And you can see that at the last year, we are showing spin squeezing at the clock fractional frequency of 10 to the -17. But the latest result, as of a few weeks ago in our lab, we have pushed this performance by a factor of 10. So new results are coming. I think it's actually a super exciting time to look at entanglement, quantum metrology, time measurements, and the fundamental physics altogether. And as I mentioned, the spin squeezing is one way to scale up system. The other way is to just simply scale up the atom number as much as you can. And here shows the picture again where we create a three-dimensional optical lattice. And if we can pack in 1 million atoms in this optical lattice systems with coherence time of 120 seconds, then in principle we can achieve clock performance at 10⁻20 at 1 second. And that would be amazing performance that we can have. Remember, the gravitational redshift at 10⁻20 is only 100 micron. And so if I average from 1 second to 100 second, it will already measure the gravitational redshift at 10 micron scale. And it's also quite interesting if you think about LIGO, when they detect the gravitational wave, they were talking about string sensitivity, fractionally speaking, of 10⁻21, 10⁻22. So clocks at this level of 10⁻20, if you average for a few hundred, a few thousand seconds, you were starting to be getting into the 10⁻21, 10⁻22 level. So it's quite appealing to continue to think about the scaling, and I'm not talking about entanglement in this regime. This is just number scaling kind of game we are playing. But of course, by densely pack so many atoms in optical lattices, the traditional way of thinking about light matter interactions of, oh, this is just a block, Maxwell block equation describing how the light propagates through a medium, that picture breaks down because atoms start to interact. The photons, as they propagate between these atoms, you start to have a radiative coupling between them and so on. This turns into a really interesting problem. And that's what I wrote here, quantum simulator and quantum sensor all building together, because this start to resemble a condensed matter system also. And people start to use the so-called Fermi-Hubbard model to describe how the dynamics of a system like this, when you put individual fermions one by one in the optical lattices with such a low energy and relatively low potential barriers between them, you can have tunneling, you can have defects, you can have dipole-dipole interactions. And so it becomes a kind of a really nice playground to look for emergence of many-body physics. And I use one equation not to scare you, just to show you that this kind of classical outstanding Hamiltonian condensed matter physicists write down for Fermi-Hubbard model is not what we need to write down for a crystal like this that we study. And there's a range of physics that we are studying, like spin orbital dynamics, spin exchange interactions, collective dipole couplings, and so on. And it's just becoming a really interesting playground for quantum many-body physics. But if we say, I just want to continue to scale up the clock performance, the ultimate scaling really maybe come back from what we learned from nuclear physics back in the 50s and the 60s in the mass power spectroscopy. And I would even argue the mass power spectroscopy is what taught atomic physicists that you can avoid the recoil problem. Here you have a gamma ray that's being absorbed by a nucleus, and the recoil of the gamma ray photon is absorbed by the entire crystal. And you can see this picture of Weiland's group when they have a single trapped ion in a regime where the trap is relatively strong. The single photon, when exciting the single mercury ions, the recoil shift is suppressed due to the fact that you have a trap that's so strong, and it takes away all the recoil shifts. And if you think back, also our optical lattice is really following the idea of trapped ions, except making many, many parallel copies of these atoms. Again, the idea that the recoil is being absorbed by the trap itself, but not by individual atoms. The difference between atomic clock and the mass power spectroscopy is that mass power spectroscopy so far is always done in the incoherent regime. There is no coherent gamma ray or X-ray photons that allow you to do coherent nuclear spectroscopy. But can we actually change that? Can we use laser to do mass power spectroscopy? And that's the question. If we can do that, then you can use nuclear structure to build clocks. And so if we make a quick comparison between nuclear energy level, atomic energy levels, will tell us quickly where the challenges lie. In atoms, as I spend most of my lecture being telling you about is we're looking at energy difference between electronic orbits. And typically we use EV scale energies. And that's the reason why we use visible photons to bridge the energy gaps between these different orbitals of electrons. And there we have a fantastic laser tools that was developed in the late 50s and early 60s, and we have enjoyed 60 years of a renaissance in atomic physics, mostly because of the laser tools have become so fantastic. On the other hand, for nuclear transitions, we still have to use X-ray, gamma ray, kind of a big user facilities to be able to do these mass power spectroscopy and so on, because only synchrotrons and so on, those are large facility photon sources, provides the relevant energy scales to excite this nuclear transition, which is typically at an MeV scale. But there is one special nuclei, and I hope there will be actually more nuclear material. This is the thorium-229. And if you look at this particular chart that shows the half-life of the excited state of a nuclear state as a function of the energy, thorium has this very low energy transition at 10 eV and happens to live also for a long time, 20 minutes or so. And so 10 eV feels like it's maybe within reach of our laser technology that we will be able to see this nuclear transition. And of course, we don't really have technology yet to be, once you can go above 10 kilo eV, then there will be a lot more nuclei will coming in. But thorium is an interesting story that the reason why there's a two low-lying states, ground state and isomeric metastable state, is because somebody observed there's a pair of gamma rays that is nearly degenerate. And they calculated the difference between the two gamma rays, and they found out, well, there must be a very, very low-lying state just above the ground with a difference of about 10 eV. What if there are other nuclei that have something similar? In any case, so now I'm going to focus on the thorium nucleus. And just recently, the group of Eka Pike and also group of Hudson at UCLA, they were able to use lasers, a very broadband lasers, to directly drive such a nuclear transition, and showed indeed you can actually see the fluorescence photons coming out of this excitation. And the laser was broadband, so you can see the line width is on the order of 20 gigahertz or so, and far shorter than the perceived or than the predicted lifetime of 20 minutes. And so what we need is to build high power narrow line with VUV lasers to be able to really go in and do precision spectroscopy on this nucleus. And this is the story of how to build a phase coherent vacuum ultraviolet frequency comb. And so I want to tell you again, this spectrum, and remember I showed you earlier about this entire electromagnetic spectrum. The visible part is where we have developed this frequency comb. When I say we, really it's I think to the two pioneers of Ted Hinch and Jan Hall, who showed that if you can precisely control the period of time of a train of ultra short pulses, and not only control the pulse to pulse period, but also control the electrical field underneath the pulse envelope, the so-called pulse carrier envelope phase over every single pulse, then we should be able to create in the frequency domain a precisely controlled grid of frequencies called a frequency comb. And this will act as a tool that allow you to translate laser phase into the microwave in a completely phase-locked fashion. It's almost like building a reduction gear with 10�6/1 without missing any single tooth as you rotate the lasers or rotate the microwave. And this technology we use every day for optical atomic clocks, but we don't have such technology yet in the VUV XUV spectral domain. And what we need to make is a frequency comb in the VUV domain. And fortunately, there's another set of pioneers who've been working on the so-called attosecond physics. And these attosecond physics people were able to generate single pulse with such a large intensity or such a large electric field. You can, when upon shining onto an atom, you can distort the Coulomb potential so much the electron will tunnel out and get snapped back in, gets so-called recombined. During this process, it emits odd harmonic numbers. And in fact, if you synthesize this together, you can actually reach the time scale of just tens of an attosecond. This is what so-called attosecond physics is coming from. So it's a time domain technology that allow you to probe exceedingly short time scales, even shorter than a femtosecond. And in order to do that, this pulse has to be of very large amplitude. And so the energy scale, typically people do such experiments is at a hertz or kilohertz scale of a repetition rate. And a single pulse like this does not provide a frequency comb to do high resolution spectroscopy because the harmonics, basically the width of each harmonic is the width of the entire visible spectrum. But what if we can repeat this process coherently over and over and over? And so if I have a one laser pulse and I waited for 10 nanoseconds, apply another laser pulse, and I just keep doing this. If the attosecond process is actually coherent, then we will be able to generate a spectrum of those high harmonics, but underneath with a frequency comb structure in there. If we can do this, then in principle, we can make a VUV frequency comb. So it's a beautiful combination of time domain, extreme nonlinear optics, and the frequency domain, very precise optical phase control. Combining them together allow us to do this. But the only challenge we must deal with is the overall power is huge, right? Each pulse energy is tends to be you need to reach electrical field of 10 to the 14 watts per centimeter squared. And that's the intensity that you needed to have, and you have to repeat this every 10 nanosecond. There is no such laser technology out there. So back in more than 20 years ago, the idea we came up with was, what if we have an empty Fabry-Perot cavity with a free spectral range matches with the repetition frequency of the pulse laser, such that every single frequency component is resonantly enhanced by the cavity mode. So it's essentially having an empty cavity where the laser pulse is built up, and the repetition rate repetition frequency is matched to the round trip time, the inverse of the round trip time or the free spectral range, such that pulse just gets stacked up on top of each other in a coherent fashion. And in doing so, we were able to finally achieve enough power and with a high repetition frequency for generating extreme ultraviolet frequency combs back in 2005. When we first demonstrated this technology, the power was, the XUV was at 1 picowatts. Now we can finally, after 20 years or so, we finally have got to above milliwatts. And finally, we can use this to look at a nuclear transition. So I know my time is probably coming up. Maybe in 2 minutes, I will wrap up. But I want to show you a very exciting new recent result where we finally got some crystals doped with thorium-229 in calcium fluoride. And this special crystal was developed by Thorsten Schumann of the Technical University of Vienna. I should say Eric Hudson's group at UCLA has also been developing thorium-doped crystals in a different host. And the one that we are using is from Technical University of Vienna. And when we put these crystals in here, we scanned it over with our VOV comb, and it's actually very beautiful, sort of a parallel scanning. We have a nuclear transition here. We can use the frequency combs since we don't know where it is, we can just move the frequency combs around. And in doing so, one of the comb teeth is going to hit the nuclear transition. And actually, in fact, we hit more than just one nuclear transition. We hit, in this case, you can see 6 of them. And the reason is not because of there's a multiple nuclear states that we're exciting to, but rather there's a nuclear quadrupole splittings. And it is indeed in multiple nuclear states, but they all belong to the one single isomeric excited state. And these lifetimes are indeed very long, and we can show that upon excitation, if we shut off the laser, the fluorescence does not decay away for basically 10 minutes. And when we look at the laser, the splittings, it's actually telling us that these nuclei are doped inside the crystal. The crystal has electrical field and electrical field gradient. And so the nuclear quadrupole moment gets split by under the electrical field gradient, and that gives rise to these 5 transitions that we observed here. So this one experiment allows us to essentially measure the difference of the nuclear quadrupole moment between the excited state and the ground state. So we are doing actual nuclear spectroscopy now with high precision. And in fact, it's quite a unique where we can measure the ratio of the quadrupole moment and translates this directly into the volume difference between the excited isomeric state and the ground state of the nucleus. And it show with the, 5th digits after decimal that the volume is different. And this is quite interesting, has implications because inside the nucleus, it's a balancing act between Coulomb interaction and strong force. And so what we are seeing is even though we're observing an 8.4 EV excitation by the laser photons, the difference of the Coulomb interaction energy is actually on the scale of 50 kilo EV. So we can imagine now starting to use this as a probe for fundamental physics. Suppose the fundamental fine structure constant alpha is not really a constant, or suppose we have coupled into the dark matter, the alpha is changing. We can actually measure this with the higher sensitivity because of this gigantic Coulomb interaction energy upon which we are seeing this 8.4 EV nuclear transition. So in order to do that, we need to keep a long time record. So this is going back to the time we need to keep a record between atomic clock and the nuclear clock and measure their frequency ratios of a long period of time. And fortunately, we have these frequency combs. We are already connecting strontium atomic clock in our lab to nuclear clock directly. And over the time, we have data now for 6 months already, and we're over 3 different crystals. We're showing the frequency records. And this is the beginning of a new field. We are very excited about continue to push on what we can do with the nuclear clock, because in the end, nuclear clock are the ones that is much less sensitive to the environmental perturbations, and potentially for portable, transportable clocks, they will be easier to handle than atomic clock. So I want to end here with a kind of a historical notion of connection back to the fundamental physics. Mossbauer spectroscopy here, pictured here in Mossbauer, it was actually the experiment where 2 physicists in Harvard, Pond and Replica, in 1960, did this very famous experiment, first time confirming the gravitational redshift on Earth, where they used the Mossbauer spectroscopy having an emitter in the basement of one of the Harvard buildings. I think the Lyman Laboratory is where the Lyman Laboratory is where they did this experiment. The bottom of the building is the emitter, and the gamma ray photon goes all the way to the top of the building, and it gets absorbed there. And they can measure the energy difference between the emitted photon and absorbed photon. And of course, I mentioned to you that with atomic clock, we can now measure this energy directly measure this gravitational redshift on the clocks at a scale of not over 22 meters, but over maybe 200 microns. That's a great connection of a precision metrology. But with the opening of nuclear clocks, the doors is even more wide open now to directly using nuclear clocks itself to further probe these fundamental connections between quantum physics, gravitational physics, nuclear physics, and so on. So I want to acknowledge many great students and group members in the group, including two students and a postdoc working on strontium 1 system to measure the gravitational redshift effects, to the strontium 2 group, which use quantum degenerate gas of atoms in the optical crystal, three-dimensional optical crystal, to study emergence of many-body physics and clock, as well as a spin squeezing clock experiment I told you briefly about, also by a fantastic group of students and postdocs. And then stable lasers. Without them, we can't really drive all these fantastic quantum coherence and putting them under control for clock applications. I have also enjoyed many long-term collaborations with the people both inside JILA, like Anna Maria Ray, and as well as people from distance, like Mariana Safranova, Michel Lukin, Peter Zoller, and so on, as well as PTB with the German Standards Lab in Braunschweig, Germany, and the NIST Time Frequency Division. Thank you very much for your attention.
Well, thank you for a very interesting talk. Do we have any questions for Dr. Ye?
Maybe I stop share just so that I can see your face better. And I'm going to run to turn on my office light really quick because I've been sitting here talking for a while and my office turned off its light automatically. I'll be right back in 5 seconds. Okay.
Got to have enough motion to keep the lights on.
Yeah, yes, exactly.
We had a very interesting talk last month from Nicole Halprin. I don't know if you know her. She's a theoretical quantum physicist who works at NIST Gaithersburg, working in understanding the nuclear, the quantum properties of groups of atoms and stuff there.
Okay. In low energy or high energy?
In Gaithersburg.
Okay.
She works at a similar joint adventure between Gaithersburg and University of Maryland, College Park.
JQI, right? That's an institute that the NIST was building, actually a little bit modeled after JILA. They want to build another joint institute, a joint quantum institute called JQI.
Exactly. They saw what wonderful things you were doing out there in Boulder, and is there any way of getting an entanglement with another group?
Yeah, no, it makes a lot of sense. I think the success of JILA really can be traced back to this amazing marriage between NIST and the university, because the people like me, I'm a federal employee actually, but we can be a little more flexible in terms of applying for grants, doing different kinds of physics, while still have NIST mission in mind. In the end, we're advancing the metrology frontiers that NIST really cares about, but doing so with a lot of fun physics. And I think that's really quite amazing and powerful. Hopefully this will continue.
We do have one question from Chris Gould. He wants to know, what are the limits now on time variation of fundamental constants, alpha in particular?
Yeah, thanks, Chris. I think the best limits have been placed on, and in fact, by German scientists at PTB, by comparing they have been running some of their ytterbium ion clock, and one of the transitions is very sensitive to the alpha change. When I say very sensitive, 6 times more sensitive than traditional optical atomic clock like mine, strontium. And so they can, in fact, set the limit of 10 to minus 18 per year is the upper limit. Nobody has seen the variation of fundamental constants. Nobody has. And so the way to see it, if the fundamental constants is changing, you have to compare two things to be able to see something's changing, right? And so what typically people have been doing is comparing two different atomic clocks, understanding that in different atoms, they have a different relativistic correction. So the dependence on alpha, the readable constant dependence on alpha is not just alpha squared. There's a modification to that coefficient. And that's where the sensitivity is coming from. When you're comparing different atomic clocks, you're trying to see whether the frequency is drifting apart or being modulated by some sort of a time periods. Nobody can really see, argue, or convincingly show that we have seen anything that the two atomic clocks are drifting apart. Usually when they do drift apart, it's because of a technical origin. But if you did things really right, things are being kind of constant, but that allow you to place a limit of how much fundamental constants may have drifted. Now, with the nuclear clock, this picture will change drastically because the nuclear clock will have sensitivity to alpha change by 10 to the 3, 10 to the 4 orders of magnitude. So this is much more sensitive for a reason. That's because, again, that's what I was trying to explain. Inside the nucleus, the Coulomb interaction energy is much stronger than in atoms. So the idea here is if we can get nuclear clock is at the very beginning, it's not even close to the level of atomic clock precision. But if we continue to develop this over the time, then if you can get to nuclear clock at the level of 10 to minus 15, you can already surpass the best limit today was set by atomic clock. And that's one of the reasons why when you bring a new technology in or a new piece of physics that's brought into under precision microscope, there could be a new opportunity to look for this kind of a new physics.
Wow.
Okay, Rudy has a question.
Chris says, okay, thanks.
Yes,
Okay.
I enjoyed the talk, but thank you. Am I still talking?
Yes, I
Yeah.
can hear you.
Yeah,
Einstein. Okay, Einstein said that the speed of light is the same in all inertial frames of reference,
Yes.
and I claim that that he got that a little bit wrong. It's the same in all vacuums frames of reference. Any frame of reference that has no attenuation, speed of light is exactly 29.974268 centimeters per nanosecond, which is almost a foot per nanosecond. And I think this is a better way of thinking about it than the gravity affects light and so on. And in fact, gravity does affect light, but it'll be exactly the same in all. And this gives the relationship between space and time. And we need one more concept to make it work exactly right. And that is that the speed of light is isotropic. It's the same in all directions. And the speed of light is not a field, it's c squared is a field. And there's a different value for it at each point in the universe. And the other field is the attenuation field, which is zero in a vacuum. I think that everything we have, there's something slightly wrong with it, and I'm trying to work out what it is, and what the correction is.
Okay, I certainly am not aware of you said the loss field. that's something I
The
don't know.
attenuation field.
Attenuation field, yeah. I can say that
And-
all the measurements we have done so far are consistent with the framework of the general relativity. In the different interpretation of whether you say the photons gaining energy or losing energy, or you say the two clocks at a different elevation have slight different clock. That's if it's just the different ways of looking at the frame transformation, right? In the end, you have
Okay.
observer. You're looking at under the metric of the gravitational field, right? And that's how you can compare two things.
Mhm. Well, I got this, I did a simulation of underwater sound and basically wave propagation on a massively
When you have
parallel
an index
computer
of
connection
reflection, that's a
machine.
different story, right? Yeah, when you have index of reflection, the speed of
Well,
light.
yeah, but the speed of light is when you change, you get an index of refraction when you change the speed of light in a substance. But my simulation showed that you needed c squared as one field at every cell on the in the simulation space, and an attenuation factor as another field, and these together gave you very realistic simulations of what actually happens.
Okay. Is there something testable?
And, yeah,
Our clocks certainly do not survive in water. They live in vacuum.
well,
Well, nuclear
I know,
clock
but
live in a crystal, and there can be an index of
but I
reflection.
was simulating underwater sound, so I had to deal with the changes in the wave speed, and basically it's more well, it's the changes in the wave speed and so on, and gives you the elongation of a tree that's fallen into the water.
Yeah, no,
You see it
that's a
bend.
problem people have worked on before, right? You know, when you have an index of refraction, you no longer have the speed
Yes.
of light in the vacuum as a limit.
Well,
So
yes,
yeah.
yes, but the physics has to do with the two fields, and if one of them is zero, then you have a vacuum.
Okay.
Because the attenuation is zero, that's your vacuum. But
Sounds good.
it's really coming up with what you need to come up with a fairly sensible simulation.
Okay.
And yeah,
So it
and
doesn't feel like you're asking
the
a
fact
question.
is you need to have that. The simulation was based on Huygens principle, that all of the energy that comes into any small neighborhood comes out of it in all directions. And you get the wave phenomena from that. Okay.
Well, thank
So,
you for
thank you
a
very
good
much.
talk. We got other chats. Art Pallone says, thank you for sharing everything. So we enjoyed it very much.
Well, thank you.
Wonderful talk. Thank you.
Thank you. Thank you, everyone.